We now go to the second step. We need to define the charge element dq or the line charge. It should be clear that charge is distributed only along the x-axis with a constant linear charge density defined as lambda, which is supposed to be a function of position, but in this case, because it's uniformly distributed, it's a constant. So picture-wise, I see a line. Excuse me. So I see a line, and it has to be symmetric. And the key thing here, if it's uniformly distributed, that means here that if this is x equal to 0, the amount of charge to the left and to the right should be exactly the same. So I have charges that have a uniform density. Now, here's what we have to start doing. By the way, I should mention that this distance right here, because I want to choose symmetry, I'm going to choose my lines to be, if this is x equal to 0, then half of the line is to the left, half of the line is to the right. Now, we need to be careful how we define this charge. So when I look at a single charge, I'm going to pick a point. And that point, I'm picking a tiny, tiny dq that is located where? So if I look at the distance from the origin, it's at the point x and y equal to 0. So I've now located a single charge element. So here we go. For a constant charge density, this means that lambda, which is a constant, so if I took the charge density of the whole line, and you could see me writing total like this, and this is the charge density for the whole line, that this is also equal to the charge density distributed at dq. So that means that if I look at a charge element dq, it is contained within a distance dx. So the key thing here is that this guy is an infinitesimal. It's an infinitesimal distance. But if the total line of the charge is q and the total length is l, then I know what that charge density is. From here, this defines the charge element. In other words, I know that lambda is constant and it's always equal to that, which then tells me that I can now solve for dq. And if I solve for dq, it's got to be lambda dx, where lambda is just the total charge over the total length of the line. So now I have my charge density. Now I go to the next piece here. So the next piece then tells me this. Calculate the displacement and the little field dE of a finite line. That's what this step is trying to do here. So let's look at that. We've already discussed that symmetry guarantees that the dE finite line field only has a y component. Even though we didn't show this before, let's do this anyways. So let's sketch these symmetry details. So here's what I'm imagining here. I have a line charge. And of course, I'm going to pick this guy to be symmetric. So I imagine that at this point right here, this is my point P. And it's going to be at the center of the line. So now what I need to do here is that I need to pick 2 points, 2 symmetric points. So I'm going to pick a symmetric point right here. And this guy here contains dq1. This line element here, which is symmetric, contains dq2. So when I start to look at the fields at point P, what do I actually see here? Well, what I see here is that coming from dq, I have a field that looks like this. Coming from dq2, I have a field that looks like this. So when I look at this thing, I see here that because they're equal distance, these 2 components automatically cancel out. So in other words, the net field of the line in the x direction must be 0. And the reason why it's 0 here is that if I pick this to be the positive and this to be the negative, that means I get a positive dE2x minus dE1x, and that's, of course, 0 right there. We knew that already because we looked at the line symmetry, which carries over to the field symmetry. Now, when I look at the y components, I can see here is that there's a y component there, there's another y component there, and they're going to add together to produce this dE line in the y direction. In other words, I'm seeing that I'm going to have two components that are going to add in the y direction. Again, dE line in the y direction is not 0 because they're not symmetric about the y-axis. So then I'm going to get dE1y plus dE2y. And as a consequence, that's what the field is going to look like. When I look at this field, what we're seeing here is that because they are the same distances, I could now only focus on one field and be comfortable with it. That is the field of the line in the x and the y direction, which is also the net field. So now we have a process now. So we need to calculate the displacement vector from the geometry. So once again, I only care about dE1y. So here I go. So I'm going to pick my line charge again. And here I am. So here's my line charge. And I'm going to pick a point P here. You know what? I think I'm going to have to lower this down. So if I pick a point P, let's see that, am I in the center? Nope, I'm not at the center. This is the center right here. So that means I have a uniformly distributed charge. So now I'm focusing only on the field produced by dq, right? I only care about the field produced by dq. But I want to look at the geometry of this. So if I look at the geometry of this, this is what I see. The distance to point P, we call that y. The horizontal distance to dq, we call that x. And you could see here that I have a displacement vector, r, which then has an angle theta. So if I look at this thing, then I have some from the geometry, I could calculate this thing. So if I look at the magnitude of the displacement, you can clearly see that r is the hypotenuse. So then r has to be x squared plus y squared square root. Now, if I look at the directional, not the angle, we don't care about the angle. We care about, look at the theta here. If I look at the theta, we can see here is that if I want the y component only, then I have to pick the opposite side. And the opposite side here is y over r, which is then r, excuse me, this is x squared y squared square root divided by y. So now I have all the details about the displacement vector. Now, you may not be comfortable in me saying that I don't need to calculate the field component anymore. But let's do this nonetheless to make sure that we're talking about the same thing. The directional of the displacement is also the directional of the field DE finite line. So if I write that DE line is equal to 2 di1y, well, guess what? I can immediately say that this sine of theta is the same as the sine of theta. Now, that may be not satisfying to you, so let's sketch the fields to make sure that it's clean. So let's sketch the fields to show that sine of theta component is picked out. So let's do that. So the first thing that we need to do is that we need to draw our line. Now, I really don't care about the left side of the line. I'm only drawing this for here, just, to try to be nice and clear with you here. But I don't need it because the only thing I care about is the field produced by dq1. So if I pick my point here to be P here, what do I see? Well, the only component that matters here is the y component. We already agreed that that y component has to be the case. So then, if this is theta right here, then I could set up a projection here where this angle must be theta as well. So when I look at this thing, I'm seeing that this is d1y, again, because that's the y-axis. This is the x. So you can see here from this triangle that the opposite side of the triangle determines dE1y. In other words, if I look at this, this is dE1y divided by dE1, and that has to equal sine of theta, which then tells us that then dE1y is then going to be dE1 sine of theta. So that tells me about the component. That sine of theta is the same thing as the directional that we calculated for the displacement. So now we could then calculate this. So to calculate the little dE line field, we summarize the details that we've already talked about. So here we go. So I have dE line has to be 2 times dE 1y. But from our previous calculation, this is dE1 sine of theta. But now if I start to look at the details here, the magnitude of the little dE is, of course, 4 pi epsilon r squared d cubed. But I have that sine of theta. So now, using the displacement, I put in all these details. And it now reads that this is 4 pi epsilon. Look at the 2. So it's now in the numerator. So if I look at the charge density, I'm going to get that this guy's going to be x squared, y squared, square root. Nope, not square root. It's r squared going into dq, which is lambda dx. So now I deal with the sign, the directional, and that's x squared, y squared, square root into y. So if I clean up the algebra, this is what I have. I have that this will be 2 lambda y divided by 4 pi epsilon naught. And then I get this integral to the 3 halves dx dE for the finite line. Now we have to calculate this thing. Finally, we're at one of our last steps, step 4. So now we need to integrate. We're going to integrate all of the little d line fields. So in order to compute the net field, we have to integrate, right? So to compute this, we have that the E of the finite line is equal to, from minus L over 2 to plus L over 2 of all of these little tiny fields. So when I look at this, note that because of the symmetry of this thing, I can also multiply this by 2 and only go after half the line and still get the exact same result. So if I look at that, note that if y is a constant, we're only integrating over x. So I can pull out that constant, which is then going to be 2 lambda y divided by 4 pi epsilon naught. And then I'm really integrating this guy from L over 2 to x squared y squared to the 3 halves. And this will then be dx. Now, this is a standard integral, and I expect that you'll be able to do this. What do I mean by expect? I expect that if you're hardcore, right? So one way to solve this is through substitution. So in this case, y is a constant. So what I would define here is that I would define x as y tangent of theta. So then you get into this trig substitution, and that's going to take you a little bit of time, but I think that's probably the fastest way to get that. Or look up the integral solution. Again, I think of mathematics as a tool. So here's the solution that I ended up looking up. It says here is that E finite line is then equal to 4 pi epsilon naught lambda L, and then I get y times the square root of y squared plus 1/2 L squared, like this. This is the field that I end up getting. So the question is, by looking at this, do we see that this calculation correct? I don't know the answer to that. So then I have to do physics now.